Hello and welcome to MJ's School of Mining and Geology Private Tutoring YouTube channel. Please don't forget to subscribe, like, and ring the bell for more videos like this. In today's lesson we are going to learn more about sample types for scanning electron microscopy or SEM. Thin sections and epoxy mounts. But others are still possible. Carbon coater. The epoxies and thin sections must be carbon-coated before taken to SEM analysis in what we call quorum sputter coater. After carbon coating, the dark sparks of carbon are produced above the sample. These dark sparks of carbon are amorphous and extremely beneficial in preventing charging mechanisms that cause material surface deterioration. They also aid in the highly efficient imaging of biological material. Scanning electron microscopy or SEM. Scanning electron microscopy or SEM analysis is a powerful analytical technique to perform analysis on a wide range of materials, at high magnifications, and to produce high-resolution images. This scanning electron microscopy is a test process that scans a sample with an electron beam to produce a magnified image for analysis. Electron microscopy is performed at high magnifications, generates high-resolution images, and precisely measures very small features in objects. Unlike optical microscopes, scanning electron microscope use electrons rather than light rays to generate images of the specimen being studied. But scanning electron microscope is still a microscope. Thus, all the features you see under petrographic microscope can still be seen in scanning electron microscope. You will see the borders of your mineral, cleavages of micas, if you increase magnification of course, textures, exsolution, and many others. SEM relies on the detection of high-energy electrons emitted from the surface of a sample after being exposed to a highly focused beam of electrons from an electron gun. This beam of electrons is focused to a small spot on the sample surface, using the SEM objective lens. There are two modes of electron detection which allows for different types of imaging and analysis, each giving vital insights. Backscattered electrons can be detected to give contrast based on different chemical compositions across an image. Secondary electrons, emitted close to the surface of the sample, give information about the surface topography. Backscattered electrons come from deeper regions of the sample, whereas secondary electrons originate from surface regions. Thus, the two carry different types of information. Backscattered electron images show high sensitivity due to the differences in atomic number. The higher the atomic number, the brighter the material appears in the image. Secondary imaging can provide more detailed surface information. Backscattered electrons are high-energy electrons used to obtain high-resolution images that show the distribution of various elements that make up a sample. When the sample is bombarded with electrons, some of the negatively charged electrons won't be captured by the pull of the positive nucleus. Instead, they'll be reflected or backscattered out of the sample. Backscattered electron imagery is always in grayscale and the color is based on the weight of the elements within the minerals. The heavy elements exhibit light color whereas the light elements will exhibit dark colors. This is because the production of backscattered electrons differs based on the weight of the element. Typically, heavier elements, because of their bigger nuclei, can deflect incident electrons more strongly than lighter elements. Hence, heavy elements like silver, which has the atomic number Z equals 47, appear bright in a scanning electron image compared to lighter elements, such as silicon, which has the atomic number Z equals 14. Because more backscattered electrons are emitted from the sample surface. Larger atoms are much stronger scatterers of electrons than light atoms and therefore produce a higher signal. The number of the backscattered electrons reaching the detector is proportional to their atomic number. This dependence of the number of backscattered electrons on the atomic number helps us differentiate between different phases, providing imaging that carries information on the sample's composition. Backscattered electron images can also provide valuable information on crystallography, topography, and the magnetic field of the sample. This image shows a simplified illustration of the interaction between an electron beam with aluminium and copper. Since copper atoms have higher atomic numbers, this will scatter more electrons back towards the detector than the lighter aluminium atoms. Thus this copper will appear brighter in the SEM image. The analogy is that the more an atom loses an electron, the brighter it becomes, but if it loses fewer electrons, the darker it looks like. This over here is magnetite with ilmenite or iron oxide X solution. Light gray is an iron because iron is heavier than titanium. The little darkest is the amphibole. Note that by increasing the silica you are decreasing the weight. The darkest is silica or felsic components, whereas the brightest will be the mafic components. Secondary electron imagery. Secondary electrons originate from the surface or the near-surface regions of the sample. They are a result of inelastic interactions between the primary electron beam and the sample and have lower energy than the backscattered electrons. Secondary electrons are very useful for the inspection of the topography of the sample's surface. This over here is a topographic information. You can see there is something on the surface here and something on the surface at the top. The rest of the sample is relatively flat because it is a thin section and it is polished. Analyses. During analyses you must be on backscattered electron. This is because that gives you the composition of the sample, whereas secondary electron gives you only the topographic information. Point and shoot gives you the composition of a certain mineral. For example, looking at point 1, on the right-hand side there will be a spectrum reflecting that point. Thus, the point, as you can see, comprises calcium, silicon, magnesium, aluminium, and oxygen. But silicon and calcium are higher in proportion. Then our results can be seen below in the form of a table. Another analysis is elementary map, which gives you map that have got different compositions. This is what the results will look like after running a map. There are areas which have higher silicates and low silicate, more iron, and more titanium. This brings us to the end of our lesson. Please do not forget to comment in the comments section below if there is anything you wish us to cover in our next video, or simply email us at malabatamorica@gmail.com or give us a call on this number 071-336-5036.